So a network of qubits entangled together, just like a quantum computer. Out of that, we suspect that space and time might...
Renowned physicist Brian Cox once said, "Quantum mechanics is deeply weird, but it works. But what if it suddenly started working in ways that even the world's top scientists can't explain?" The Majorana 1000 qubit quantum chip isn't just setting new records in computational speed. It's behaving in ways that challenge our entire understanding of physics. Researchers have observed qubits that seem to rewrite past data, anticipate future outcomes, and persist in superposition states far beyond what should be possible. Is this the next great leap in quantum technology? Or have we unleashed something we can't control? The Majorana 1000 qubit chip. A breakthrough or a crisis in the making? The Majorana 1000 qubit quantum chip was supposed to fix one of the biggest flaws in quantum computing: decoherence, the tendency for quantum states to collapse unpredictably. To solve this, scientists turned to Majorana fermions, mysterious quasi-particles first theorized in 1937 by Ettore Majorana. Unlike normal particles, these are their own antiparticles, a bizarre property that allows them to store quantum information in a way that's far more stable than conventional qubits. With this breakthrough, researchers anticipated a new era of quantum supremacy. A computer with this level of stability could unlock breakthroughs in encryption, artificial intelligence, drug development, and even materials science, achieving things impossible for today's most advanced supercomputers. But what started as a technological milestone is now bordering on science fiction. The chip's behavior is so strange that it's defying every expectation. Calculations that retroactively change past inputs, as if rewriting reality itself. Qubits that remain in superposition far beyond known physical limits. Solutions appearing before their problems are fully defined. These aren't just glitches, they're systematic and repeatable, and no one knows why. Are we witnessing the birth of a new branch of physics? Or have we stumbled into something far more unpredictable? The scientific community is divided. Some see opportunity, others see a Pandora's box we might regret opening. Quantum computing is producing solutions before problems are fully defined. How is that possible? In one of the most bizarre findings yet, researchers observed something truly unprecedented. The Majorana 1000 qubit quantum chip solved complex problems before all input parameters were even entered. Let that sink in. The quantum processor wasn't just computing answers, it seemed to anticipate them. In one experiment, scientists ran an optimization algorithm meant to solve a highly complex mathematical problem. But before the conditions of the problem were fully defined, the chip had already produced the correct solution, as if it had somehow skipped ahead in the process or accessed the final outcome before the computation was complete. This behavior is not supposed to be possible under our current understanding of quantum mechanics. It suggests that the chip's qubits might be engaging in a form of predictive computation, operating independently of traditional cause and effect constraints. So what's actually happening here? Are we seeing a new emergent quantum property? Could this be a form of entanglement that extends beyond known physics? Or, as some physicists now speculate, is this quantum system tapping into something much stranger? An alternate reality? Three theories behind the anomaly. Are we witnessing a new form of computation? Since no classical explanation fits what's happening, physicists have proposed several bold hypotheses. 1. Enhanced quantum sampling, predicting the future? One possibility is that the 1000 qubit Majorana system is so advanced that it can extract hidden patterns from the input data, predicting the most likely solution before the entire problem is fully processed. This would be an extreme version of Bayesian inference, where the quantum state collapses toward the most probable answer before all classical information has been entered. In simple terms, this means the chip may be predicting the most statistically likely outcome before it actually runs the full computation. If true, this would be one of the most powerful predictive technologies ever created, with enormous implications for everything from AI-driven forecasting to financial modeling, scientific simulations, and beyond. But what if the explanation is even stranger? 2. Quantum time symmetry. Can the future influence the past? Another theory suggests that the chip is leveraging retrocausality, a controversial concept in quantum mechanics where future states influence past states. While it sounds like science fiction, Some interpretations of quantum theory, such as Wheeler-Feynman absorber theory, suggest that under extreme conditions, quantum information might be able to travel backward in time. If that's the case, then the Majorana chip isn't predicting solutions at all. It's simply receiving them from its own future state. Imagine a system where the answer already exists in a later computational step, and that information somehow leaks back into the system's earlier state. If this is happening, it could rewrite the way we think about causality itself. But what if the chip isn't just drawing from different points in time? What if it's pulling from entirely different realities? 3. Multiverse computation. Are we sampling solutions from parallel worlds? The most radical explanation suggests that the quantum processor isn't just running calculations. It's selecting solutions from pre-existing probabilities across multiple realities. According to the many worlds interpretation of quantum mechanics, every possible outcome exists in a superposition until an observer collapses reality into one definitive state. What if, instead of generating answers through computation, the chip is simply reaching into parallel quantum states and retrieving the correct solution? This idea is deeply controversial, but it's not entirely without precedent. Some quantum theories suggest that certain systems may be able to interact with alternative quantum branches, meaning we could be seeing evidence of computation across multiple dimensions. If true, this wouldn't just redefine computing. It would redefine our understanding of reality itself. But with such mind-bending implications, new concerns are emerging. If quantum computers can predict solutions, manipulate past inputs, or pull from alternate realities, what does that mean for the future of information security, ethics, and even free will? Whether this marks the dawn of a revolutionary new era or the beginning of a technological challenge we can't yet contain remains to be seen. But one thing is certain, the quantum age is no longer just a theory. It's here, and it's advancing in ways we're only starting to grasp. At the heart of this breakthrough is a new state of matter, something Microsoft and other researchers call a topological superconductor. This exotic material supports a rare type of particle known as a Majorana fermion, which has a property unlike anything else in physics. It is its own antiparticle. This makes it a perfect candidate for the foundation of a new kind of quantum computing, one that is far more stable and resistant to error than anything we've seen before. Why topological superconductors are a game changer. Unlike traditional superconductors, topological superconductors have unique quantum states that naturally resist external interference, things like temperature fluctuations, electrical noise, or even cosmic radiation. This makes quantum computations much more reliable. At the core of their advantage are Majorana zero modes, special quasi-particles that emerge in topological superconductors. These theoretically offer incredible protection against decoherence, meaning they can hold quantum information much longer than conventional qubits. This leads to a major breakthrough in fault-tolerant quantum computing, a goal that has long been out of reach due to the instability of existing quantum systems. Why this matters. One of the biggest hurdles in quantum computing today is decoherence, the rapid collapse of quantum states due to environmental interference. This is what makes scaling quantum computers so difficult. Microsoft's approach, using topological superconductors, could eliminate this issue by creating qubits that are naturally resistant to such disruptions. If successful, this could be the key breakthrough that makes large-scale, practical quantum computing a reality. Think of it like a superhighway for quantum information. Imagine a traditional quantum computer as a race car on a rough, winding road. The car represents quantum information moving at incredible speeds. The problem? The road is full of potholes, disturbances from the surrounding environment, like temperature changes or electromagnetic noise. Every bump threatens to knock the car off course, potentially leading to data loss and calculation errors. Now, picture a topological superconductor as a perfectly smooth, straight highway. No sudden bumps, no unpredictable turns. Just a perfectly optimized route for quantum information to travel without disruption. This means the quantum car can maintain high speeds, stay on course, and avoid data loss, making quantum computing far more practical and scalable. Majorana fermions, the unbreakable passengers. But what if something goes wrong? Enter Majorana fermions, like intelligent co-pilots that don't just ride along, but actively protect the quantum information. These particles prevent interference from external forces. Even if the system encounters disruptions, Majorana fermions keep the quantum state intact. In essence, they function as both the driver and the security detail, ensuring the car never loses control. The big picture. What this means for the future. If Microsoft's approach proves successful, we could be looking at quantum computers that actually work at scale, not just in theory, but in real-world applications. Breakthroughs in cryptography. Quantum computing could crack today's most advanced encryption, reshaping global cybersecurity. Revolutionizing artificial intelligence, AI, could process unimaginable amounts of data with quantum-powered models. New cures and drug discovery. Simulating molecules at the quantum level could lead to medical discoveries never before possible. Advanced materials and engineering. Quantum models could help design stronger, lighter, and more efficient materials for everything from spacecraft to everyday electronics. The big question: is this the key to quantum supremacy? Will Majorana qubits finally break through the barriers that have kept quantum computing from becoming truly practical? Or will new, unforeseen challenges emerge, forcing researchers to rethink their entire approach? Let's hear your thoughts. Do you think topological superconductors are the missing link to quantum supremacy? Drop a comment below. And if you want to stay ahead of the biggest scientific breakthroughs, subscribe now for more deep dives into quantum mechanics, space exploration, and cutting-edge technology. Because this is just the beginning.